What's cooking? What are we dealing with here? Questions? Wow. Yeah. It's a conversation stopper. I'll have to use this the next time. Yeah. We had a dinner party and somebody just start talking and say, hey, anybody got any questions? And then we would... Okay. I asked you last time in party, and I gave you, we've already done this question about the electric potential being the highest. What I was wondering about, though, I think I left you with the parting question about where is it zero? Right? Okay, there we go. Make sure that I'm actually projecting it to everybody. So I said, yeah, I sit there, ponder at lunch, see if you can come up with the location or locations on this, topographical map of the electric potential. See if you can come up with a location where the electric potential is zero. Have you managed to do that yet? Have you identified a location where the electric potential is zero? Even though I haven't labeled them, right? What say you?
On the AED line?
Yeah, along the ABD line. Yes, exactly. You say, well, how did you get that? Bear in mind, we're dealing with the dipole here. We have the plus charge as blue as the negative charge, even though we can't see it. So that's number one. Remember, we're dealing with the dipole. And you notice that the line that A, E, and D are on, notice that that is essentially halfway between the dipoles. Right? Very important, halfway. In other words, if I choose any location on that line, let me get a color that might actually show up on black here. If I choose any location, say right here on that line, I am the same distance away from the positive charge as I am from the negative charge. Say, well, how does that help me? Let me now write down the expression for the electric potential. We had it down here in this lower right-hand corner at some point, but I'll write it here just to remind us. The electric potential is given, the electric potential due to a source charge is given by the Coulomb constant, the value of the source charge divided by the distance to that source charge. And just like the electric field, just like forces, the electric potential will also obey superposition. So if I want the total electric potential at, say, this field point that I've chosen, I can add up the potential, the electric potential due to each of the individual source charges. The source charges are the same distance away, and they differ only in charge. One's positive, one's negative. So if I add the two together, I end up with 0, right? Same distance, Coulomb's constant is the same for both. The only thing that differs is I put in positive Q for one of the charges, I put in negative Q for the other. And then when I add them together, I get 0. Yeah, good. A different way to think this, if you want to think about it in terms of, again, elevations or kind of more visually, I have a peak and I have a valley that are exactly the same height. Halfway between, I should hit sea level. All right, if I have a 1,000-meter peak and a 1,000-meter valley, and they're exactly the same shape, then halfway between, I must be at sea level. So you can get, point E is at sea level, and point E lies on an equipotential, so that entire line must be at 0. Yeah, nay? Yeah, I mean, sort of.
is E at the highest electric potential?
E has the highest electric field. Right, sorry, maybe I misspoke on Wednesday. E would have the highest electric, it's the location of the highest electric field. And how do we get that again? Based on this stuff? If I give you the electric potential, how do you figure out the electric field?
That's where the lines are closest.
Where the lines are closest together. Remember, if we have a map of the electric potential, we can use the spacing of the lines to the visual spacing of the lines is indicative of a slope. The steeper the slope, the higher the electric field. The larger in magnitude, maybe I should say. So yes, the slope conveys how strong the electric field is at a particular location. And that's what you'll be mapping out on Tuesday. We don't have good device. I mean, the electric field, I guess you might be able to measure it directly, but in reality, you use devices like this. And this will measure the electric potential difference between two locations. Or, I mean, this is analog. This is the digital version of it, right? This is just what's called a digital multimeter. And one of the things it can measure is the little V right here. This is V, I turn the knob to V. And what that will do is it will measure the difference in electrical potential between the two probes. So I stick this one place, I stick that another place, and whatever it reads is the difference in electric potential between those two probes. And you can say what's going on in here, to be continued. Okay. Turns out there's a little, if you really want to know these analog units, there's a little spring that's attached to a small magnet, and it's very sensitive. You say, well, why does that come in? I'll say, to be continued. We haven't got to that part of the physics yet. So, but yes, it's very easy to measure. We have devices that can very easily measure the electric potential. And so if you want to get an idea about the electric field, which again, you will also do in lab, you start by measuring the electric potential, you create your topographical map, and then you extrapolate the magnitude of the electric field. Now, bear in mind, when you're doing it in a lab, you'll be able to say, okay, this line is at 5 volts. This one's at, as you map out, you'll say, okay, well, let me find the positions in space where it's 10 volt difference and draw it out. So you'll have actual numbers for each of these equipotential lines. And so you can actually do a little bit more. Sorry, preface, foreshadowing. You have numbers for each of those equipotential lines. It'll be on a physical piece of paper, so you'll be able to measure the distance between the lines. You'll just put a ruler on the paper. So you'll have values for the equipotentials. You'll know the distance over which the lines have changed. You could actually calculate out the electric field strength. Experimentally. You don't look thrilled by this.
Is the electric potential for A and D 0?
The electric potential at A, E, and D are all 0, yes. They all fall on the same equipotential line. And it's the same thing. This is for a dipole, but you could do this experimentally. You could do this for any kind of charge arrangement that you want. So there's mapping boards. It's called a mapping board. But essentially, you put some charge arrangement on the backside, you measure the equipotentials, and you can kind of get an idea of what the charge arrangement is without actually looking beneath the board.
Are B and C equal, or is the negative positive?
B and C will have the same magnitude, but they'll be opposite in sign. Yeah, this one will be below sea level, if you will, below 0, and B will be above 0. And you can see, excuse me, going on with that discussion about distances, you can see, if I'm considering field point B here, so I'll write out V total. will equal, I'll put K, the positive charge and the distance to the positive charge. And you notice that this distance is a lot smaller. And I'll put in the second one, plus K negative Q, distance to the negative charge. So this is R positive here. This distance would be R negative, right? The distance to the negative charge. Which of these two terms is larger? Is the first term the larger term or the second term? The first. I divide by a smaller number, the first term must be the larger term. Which means you'll get something, a big term minus, right here, minus a smaller term. You'll get something greater than 0. Now, the opposite, if you go down here to location C, then it's the second term that's larger. And so you'll end up with a value that's less than 0. Does that answer your question? Yeah. Yeah, we're kind of working on the 30,000 foot view, right? I'm not giving you numbers yet. I'm trying to just build the conceptualization. Yeah. It's kind of hard to do it with 2D plots. It's the 1D ones that you can, 1D, you can, look at it and see the slope right away. Anybody? Not that it's a requirement, I was just curious. Anybody taking Calc 3? Okay, I was just curious. That answer. Nobody's like, oh yeah. Okay. Do you ever hear, anybody heard the term gradient? Okay. The gradient is how you do the slope in 2 dimensions and 3 dimensions. So, where does the gradient come into play? Thermal or?
There's no gradient based on landscapes.
Oh, okay, yeah, it's the exact same idea. Yeah, the gradient, so if you do geology and you're looking at the gradient of the land, that's mathematic, there's something called the gradient from math. Usually you see it in Calc 3, but it's a way of calculating the slope when you're dealing with a 2-dimensional surface. So yes, geology tends to use the word gradient and calculate a lot just because they're doing a lot of 2-dimensional surfaces. Usually when they're thinking about watersheds, right? It rains, where does the water go? It follows the gradient, the steepest slope is what it does. So anyway, yeah, that's okay, that's well off topic. Other questions? You guys okay?
No.
No. Brutal honesty.
You asked. I answered.
What? Yeah. Just tired?
So tired.
Yeah. I mean, I can go and egg my neighbor's house if that makes you feel better. I
Your
mean,
neighbor is actually my coach, so that would actually be really fun.
yeah, I figured that would make you feel better, right? Yeah.
I
No.
ran into a blizzard the other day, so I really appreciate it.
Yeah, I know. I think did I run by that day or did I walk by? I can't remember if it was on my walk or my run, but I heard him yelling at you.
Yeah.
It was that exercise where you roll the ball and 2 people run and get it.
Yeah, we did that.
Yeah, and I think you were serving it up, weren't you?
Nope.
No, I thought he said Emily and Delaney are supposed to be serving it up or something.
Well, the lane's goalie, so that would make sense.
Oh, okay. Well then, no, I guess not. Okay. Yeah.
Oh, yeah.
So it wasn't yesterday. It was like 2 or 3 days ago. No, yesterday. Well, who was out? The soccer team was out when I was walking in the morning.
You were out when you were running by, because I saw you.
The men's lacrosse team was out when I was running, I think, last night.
Yeah, we were on the other side of the field.
Oh, okay, yeah. Okay, so I missed you yesterday. But it was like 2 days ago when you were on the other side of the field. Yeah.
Good job.
So you feeling better already, right?
Yeah, it's a stretch.
Oh, okay. I tried. Let's see the rest of you. You okay? Yeah. Okay. Yeah. Questions? Okay. No questions. Let's just keep going. Oh, I didn't map that yet. Excuse me. I went to my bigger tablet so Ty could use the smaller one. Oh. Yeah. But you could say something like this. Let's say I drop a proton into this thing. Where is it going to experience the largest force? This information, that force information is actually conveyed in this as well. It's just a step away. So go ahead, where's it gonna experience the largest force? That's right. Oh, that would be perfect. I gotta get like one of those little things that people put on the back of their cell phones. What is that called? The little, yeah, okay. Yeah, that's what I need. I was like, I know what's gonna happen. I'm gonna be like waving this thing around and I'm just gonna.
This one? I don't have it, I don't need it.
What do you, what? You're just like on that. I would take it, except that could be misconstrued as a bribe. A pot de vin. It's a sample. Did you pay money for that?
No, I got this for working at the admissions office.
Oh, okay, in that case, I'm taking it. Thank you. Sweet, get your grip on. Of course, now it won't sit flat when it's on my desk, but that's okay. We'll figure that out later. Oh, now I feel like I'm in the choir. I can't sing with the darn, but man, I feel important now. Okay. Where do you experience the largest force? That's. Thank you. Sweet. I'm gonna have to get like 5 more of them and put them on the corner so that when I set it on the desk, it's actually level, but that's okay. Where's the largest force?
E.
E. Why?
Because of the short distance between the charges.
Okay. Shortest distance between the charges. Okay. So you kind of went from the charge perspective.
Yeah.
Okay. Yeah. How about from the equipotential line perspective? Let's say I didn't put the charges in at all. How would you get it from the equipotentials?
I don't know if this is what you're asking, but like at E, both of like the force vectors will be pointing down, and then if you add them up, it'll just.
Yeah. So you're kind of using the idea of the charges again, right? I mean, like, how do you get the force vectors is the question. Yeah, I completely agree. Yeah. You've already answered this question. Right? Let's do this. Forget about force. Where's the location of the largest electric field? Survey says E, and I said why, and you said the lines are closer together. So you know already that location E has the largest electric field. All right? Keep that in mind. Now come back to this. Which location has the largest force? How do I relate the electric field to a force? By the charge. I take the charge I'm concerned with. Here I said a proton. I drop it into the location of the largest electric field. That location will also correspond to the largest force. Right? In other words, I'm asking you to consider this relationship. The electric field times the charge gives you the force. Right? I'll put here system. So if you can tell me the electric field, you have an idea about the strength of the electric field and the directions, you can automatically, well, with a little mental gymnastics, you can get the force. You can get the vector field for the force. Yay, nay? One plot, 4 things. So it gives you the electric potential. You can look at the slopes to get the electric fields, which are pretty much related to the forces, the Coulomb force. Let's keep going. Yeah, that's right. Okay, to fix that mapping. How about this one? At which location will a proton experience the largest change in kinetic energy? Yeah, you could go ahead and talk to your neighbors, or if you want, or you can just, yeah, that's fine too. So, navigation back. Okay, I'm back now. Let's try that again. Oh, that works so much better. I could take the swing back. Try like the sign spinning, but that's the suit. That's nice. This is the first time I've actually said, okay, that's useful. I mean, I'm sure it was useful for the cell phones, but I got an outer box, which is like carrying a brick in your back pocket, and then you put a pop top on top of the outer box. That's like, yeah, that's like Zach Morris phone at that point. Zach Morris, Saved by the Bell. Yeah. It's a really cool show, like in the 90s, you whip out a cell phone and it was literally the size of a brick.
Did you see the screenshot?
Yeah, I did. Yeah. You whip out the cell phone, it's the size of a brick, you're like, that's cool, I want one of those. You can call from anywhere? Right. Largest change in kinetic energy. Which location? E. I agree. Say why? Why is that the largest change in kinetic energy? How did you know that? Well, one way to say it is it's also the location of the largest force. One way you could do it is that. You say, well, I know that's the location of the largest force because the lines are closest together. That was the location of the largest electric field. So it corresponds to the largest force, and the largest force will give me the largest change in kinetic energy. It's pushing the most. You could go the other way. So that's, starting with the electric potential, going to the electric field, going to the force, and then going to energy. Right? If you're thinking about that square for a second, you started here in the lower right-hand corner, you went to the electric field, then you inferred something about the force, and then you inferred something about the energy. You kind of went all the way around. Right? The other way you could have gone is right straight across the bottom. Right? Let's see, what do you mean, Greg? Let me ask you this. At what location will you have the greatest change in electric potential? Survey says E. They say, well, why? You say the lines are closest together. Greatest change in electric potential at where the lines are closest together. Steepest slope still. And the question then I have for you is, how do I relate a change in potential energy to a change in electric potential? What's that relationship?
Directly related.
They're directly related, they're proportional. Yeah. And what's the constant of proportionality between a change in electric potential and a change in potential energy? The charge of the system. Yeah. So a different way is that you could just say, hey, the largest change in potential energy is proportional to the largest change in electric potential, where the lines are closest together. And the constant between the two is the charge of the system that you're putting there. Of course, if you have a large change in potential energy, you're going to get a large change in. So I didn't ask about potential energy, I asked about kinetic. You have a large change in potential energy, you're going to get a large change in the kinetic energy. Yay, nay? You follow?
Does that mean that inversely is related?
Energy goes down, then the kinetic energy is going up. Yeah. Largest. Yeah, but I was just asking for the largest change, whether it means going up or going down. Yeah. Yay, nay? Oh yeah, let's go on this byline for a second.
Is there a formula that we need to know for the kinetic energy?
Sure. Sure. KE 1/2 mv squared. Yeah, so I define the kinetic energy as 1/2 mv squared. I guess you could say macroscopic kinetic energy. You still have the microscopic one, but I'm not worried about that. Vibration of the tiny molecules that make up the desk. Okay, other questions? Yeah.
So by getting the force, didn't you like associate that to acceleration and associate that to velocity to get?
Yeah, you could go that way if you want. Or if you want, if you have the force. So if you have force, muscle memory, sorry. If you have the force, you could do something like the force times the displacement, or the parallel force times the displacement equals the work, and the work results in an increase in kinetic energy. Yeah. The only reason I don't like the acceleration path is that the acceleration could be non-constant. So I think you're probably thinking in constant acceleration, and then you can apply the kinematics to get the change in speed. Yeah, something like that. That's fine as long as the acceleration is constant. This would be kind of the more general way of thinking of it. Yep. Oh yeah, slight byline. Yeah, because this applies to the chemists and sometimes the biologists too. Yeah, imagine for a second. Let's just put some numbers on here just for, conceptual purposes. Let's say that this line, we've already argued this one's 0 volts. I don't know, what's your favorite number? 7? Okay, we'll make this one 7 volts. We'll make that a 7-volt equipotential. We'll make this one 14 volts. And this one down here, this should be -7 volts. And this one should be -14 volts. Okay, so on and so forth. Imagine for a second, I move a proton from here, this equipotential surface, and let's say that I move it to, I don't know, let's move it down to here, right there. Yeah. By how much have I decreased, well, what's the change in potential energy? Let's start there. I'm sorry?
14 volts.
It's 14, so the change in electric potential was 14 volts. Right, if I want to find the change in the electric potential, delta V, I should do my final minus my initial. Well, my final is -7, and my initial was 7. So my change in electric potential is -14 volts. What's the change in the potential energy of that proton as I move it from one equipotential to the other? It's not 0. I mean, it's essentially rolled downhill. Right. What's the change? What should I write for the change in potential energy? Incidentally, I said it was a proton.
Is that times the charge?
It's that times the charge. It's the change in electric potential, delta V. So I'll put -14 here, times the charge of the proton, E. Now, if I wanted to write in the charge of the proton, right, E is 1.6. In fact, here, I'll put this suggestively right here. And I would hazard to bet at least some of you have seen that. Right? You've seen the term EV. What is that sometimes called? I mean, full phrase. electron volts. It's a charge times a difference in potential. So sometimes you see this phrase EV, electron volts, and it is a unit of, a non-SI unit of oh yeah, that's it. Yeah, we'll have to put, that's the conversion factor. But electron volts. It's not a unit of potential, electric potential. It's not an electric field. It's not a unit of force. It is a unit of energy. Yeah. The electron volt is a non-SI unit of energy. Now, why do chemists, biologists use it? Even physicists. Right, I would go up to Argonne National Laboratory and we would run electrons with 10 keV, 10,000 electron volts. That's how much energy each electron had. Usually you'd use that because if I want to put this in SI units, I should substitute in the charge of the proton here. In other words, if I want an SI units, I should write delta U, sorry, I'm near the bottom of the sensor. I should write delta U is equal to negative 14 times 1.6, I'll leave it, O2, times 10 to the negative, step closer, negative 19, and I'll close the parenthesis, and now that's officially in joules. I don't know about you, I'm lazy. If I'm doing some chemical reaction where all this stuff is on the order of EVs, I don't want to have to keep writing this 10 to the negative 19th all over the place. I'm just going to leave it in terms of EVs. So for example, the ionization, this one I remember, I was discussing this on, shoot, what night was that? Was that Sunday? No, that was Wednesday. Yeah, we were discussing this on Wednesday night. The ionization of a hydrogen atom should be something like negative 13.6 electron volts. In other words, if you have a hydrogen atom and you want to rip the electron off of it, okay, it costs you 13.6 electron volts. You say, how many joules is that? Well, just substitute in the charge of the electron here. And I'll tell you. About 10 to the negative 17th joules. Which is probably how much energy you acquire when you breathe, when you smell the Lucky Charms at breakfast. Right? You don't even have to, well, I assume, is there any calories associated with smells? It seems like there should be. Right? There's something hitting your olfactory bulb. I guess. But I was just I mean, it can't be that big, but I'm like, I mean, you've got to be getting a little bit of calories, right? Like, you don't just smell for free. Like, something has to hit a receptor somewhere.
My Weight Watchers.
Yeah, I was just curious. Like, can you actually? I mean, like, not from a practical standpoint, no, you're not going to gain weight by smelling things. But it seems like from a theoretical standpoint, it seems to me like you should. Of course, breathing as well. Of course, you exhale, so maybe you could lose weight by breathing. And certainly celery. That one I know, right?
Yeah, it costs more calories to process it than it does produce.
Yeah, we should all go and get some celery. Right? Just, you know. Questions so far? Yeah, so when you're doing those like chemistry equations and you see EV popping in, you're working in terms of energy. You're just doing a non-SI unit. And in fact, if you're ionizing, for example, the hydrogen atom, you are moving the electron through 13.6 volts. As you move that, as you grab that electron in the hydrogen atom and you move it all the way out to infinity, you have made the electron cross 13.6 volts. You know, like you could think of the contour lines being drawn in space and, okay, there's 1 volt, there's 2, there's 3, there's 4. When you get to 13.6, the electron's infinitely far away. That's assuming there's no other charges anywhere in the universe, right? Like you just have a hydrogen atom and that's it, right? Spherical cow in space kind of thing. Yeah.
I'm like a little confused how at E we have the highest magnitude electric field and the highest force, but then the electric potential is 0.
Okay, let's do an analogy. Okay. Let's do it, yeah, let's try this one. Maybe this one will work. Your speed is 10 miles per hour. Can you be located at the origin? Yes. Right, why?
Actually, you could have started somewhere else and then.
You go to start some, I mean, the idea really is that speed is a change in a quantity, where a change in your location, delta. Whereas your location is like an absolute value, right? You're at the origin. Speed is how quickly are you moving away from the origin? What's your change in position? That would be analogous here. Okay? The electric field is related to the change in the electric potential. So I've decided we've placed the origin here. It's that the electric field is the change. As I move away from the origin, how quickly does the electric potential change? Yeah. Does that help? Yeah. And then, yeah, so your speed, you have some 10 meters per second speed. You can still be located at the origin. Right? Those are independent things.
You say electric field is the change in?
The electric field is the change in the electric potential per unit distance. It's the slope. Yep. Other questions? Like I said, it's a little harder to quantify on a graph unless I would have to actually give you like physical distances, and I'd have to give you, like if I said, well, I'd have to give you some scaling at least. Maybe if I gave you a scale bar, say something like this distance represents 1 centimeter, then you could actually start quantifying how strong the electric field is at different locations. You'd have to, sit down and get your little ruler out and say, okay, well, if this is a scaling, so this represents about 1 centimeter, and I say, okay, well, I cross 1, 2, 3, 4, 5, 6 lines. So that would be something like the change in electric potential would be something like 42 volts, because I think we said each line was 7 volts. And so you say, well, I've changed 42 volts over a distance of 1 centimeter, 0.01 meters. Sorry, that looks like a 6. It's supposed to be a 0. And so now you can quantify. You can say, okay, well, the strength of the electric field roughly at location E, based on the scaling that we've done, something like 4,200 newtons per coulomb. That sounds like a great, I should write something up like that. That sounds great. As long as you're not hesitant to put a ruler against your computer screen. I don't know, I hate my kids touching my computer screen, so I can't encourage you to do that. Yeah. Sit down, all I can see is finger marks. I can't watch Penn and Teller on YouTube, but all I see are finger marks. No, not a fan. Penn and Teller? Famous magicians? Yeah, they run a show where it's called Penn and Teller Fool Us, and so they have other magicians try to do a trick that they can't explain. It's kind of fun. Anyway. Okay, I think I've drawn enough on this. Sorry, I should have been, okay, so this is a separate idea, and, yeah, the way to correct a drawing, the way to correct a slide with too much drawing on it is to draw more on it. Okay, other questions? Okay, you already got this, beating a dead horse. Again, these maps, these contour maps, I'll say give you 2 for the price of 1. In fact, we've gone through an argument, maybe I should change the slide and say it gives you all 4 for the price of 1. As long as you can get the electric field and the electric potential, you could figure out what the force or what the change in potential energy would be, as long as you know what the charge that you're placing is. So, this one has I went back and looked. This one has a more scaled version, so you notice that as you're closer to the positive charge, you have larger arrows, and as you get further away from the charges, those arrows get smaller. So this is just a scaled version of that really crappy one that I showed you last time. Okay. So that's if you're really measuring out, finding the values of the electric fields. More often than not, you'll see it also presented like this. Again, same idea as that other junky gave you, is that you're not trying to convey information about the magnitude of the electric field, you're just conveying information about the direction. Okay. So dashed lines here would be the equipotential lines, here, here, here. And these solid lines are just giving you the direction of the electric field. It's not trying to convey the magnitude of the electric field. Okay. When you're drawing these in, incidentally, I think I mentioned this once, I'll re-emphasize it here because I know that Leo will re-emphasize it when you get to lab. The electric field lines are always perpendicular to the equipotentials. Right? Once you have the equipotential lines, the electric field lines are perpendicular to them. They always point downhill, so they'll be perpendicular. What are the other interesting things? Oh yeah, I don't know if it's worthwhile to mention or not, but like equipotential lines can't intersect. That should make some sense to you. Right? You can't have 2 equipotentials of different values intersecting. Right? That would mean that at a single location in space, you have 2 potentials associated. That's like the analogy would be if you're standing on a mountainside and you're at 2 different elevations. That doesn't make any sense. Okay. So that's the other thing that I don't know if that'll help out in lab or not, but yeah, equipotential lines don't cross. I mean, the only way that you have 2 equipotential lines that cross is if they're the same potential. And then you could have drawn the contour differently, probably. So it's one of those weird cases where I think it's easier to conceptualize when you look at 2 dimensions. It's a little harder, I think, to conceptualize when you go back down to 1D. So the good thing about 2D is easy to conceptualize, hard to get the numbers. Like hard to, calculate slopes and that kind of thing. 1D, easy to get the numbers, easy to calculate slopes. It's a bit harder to actually conceptualize what's going on. Which is why I started off with this and then I go back to 1D. All right, so. You want to take a stab at it? Given a potential, you got a little palmy thing for that pens too? No, that's not gonna work. I was just joking around. Like, this will keep me from throwing the tablet, but what about the pen? Like, maybe I need to I hope I don't break something. Okay, there it goes. I wonder maybe we should get a string so that they're all, anyway. Okay, given the potential versus position graph. So I'm thinking 1-dimensional motion right now, okay? What field point would the electrons, so notice I put an electron, potential energy be the highest? Okay. Go ahead, talk to your neighbor, get an idea. At what location, say at what distance from the starting point, the origin, which I have over here, at what location will the electron's potential energy be the highest? Go ahead, talk to your neighbor, get an idea, go. In the meantime, how's the battery here? It's looking a little wonky. No, that's okay, so I'm just getting too far away. It's probably all this electric stuff that I have sitting around here. draw it out if you want to. You could draw out the entire, once you have the idea, if you have the single question answered, you could probably redraw a potential energy versus position graph. In fact, go ahead and do that if you haven't. Such a terrible name for a rotor. If you look up really fast, that R looks like an F. And then you're like, wow. Sorry, the access point there. If you look up, the R looks like an F, and then you're like, that's a terrible name for a router. Ruckus. Yeah. It's just sometimes what the router does. Creates a ruckus. You got an idea? More time, less time? Nobody answers. What would your answer be for a proton? Just like this. I mean, I highlighted that's an electron. What would your answer be for a proton? Maybe I should say, what should the graph look like if it were a proton? If I wanted to plot the potential energy versus position and it were a proton, what would it look like? Yeah.
It would be like flips over the x-axis.
Yeah, okay. So yeah, good. You're thinking the electron now, right? Oh, the proton? Yeah, yeah. So if I have a potential, or excuse me, if I have the electric potential, I would multiply by the charge in my system to get the potential energy. So if it's a positive charge, I take my potential and I multiply by E. In fact, you ready for the potential energy plot? I will now get rid of this. I'll put it in U, and I'll put an E here. Boom. Oops, excuse me. Boom. I have now drawn the potential energy plot for a proton. I changed the scaling, but the shape stays the same because it's a positive charge, right? The only thing that happens is that instead of 200 volts, it's 200 times E, joules. So how about for the negative charge? What would change? Yeah, just the sign. In other words, graphically, what should I do? Flip the whole graph, right? If I do an electron, so that's for a proton. If I do an electron, I should do U is equal to, I'll put negative E here, V. So wherever I see a positive V, it now becomes negative. So this location becomes, okay, well, it's off screen, but that would be down here. And any place where it's negative, it should now be positive. So if I'm dealing with an electron, the graph should look something like, okay, there. You know, it's flipped around the x-axis. And scale, right? You still have to put the electron in there. So highest. At about 2 centimeters. shouldn't say about, 2 centimeters. Yay, nay? Yes. What region is the largest electric field? So let me clear off the graph here. In what range of positions is the electric field the largest?
Would be from like 2 to 5.
Yeah, would it be from like 2 to 5? And why do you say 2 to 5?
It's
2
like
to 5.
slope is indicative of how strong the electric field is.
Yeah, a slope is indicative of the strength of the electric field. So essentially I say, where's the steepest slope on this graph? You said from 2 to 5, I say, yeah. And in fact here, this is why I said 1D is easy to calculate. You can tell me what the slope is. For a 1D graph at least. Slope is, not the numbers, but how would you calculate it? Rise over run. You rise what? 300 volts over a run of 3 centimeters.
In this example, isn't the slope from 5 to 7 the same?
The slope from 5 to 7 the same. Oh, I haven't the foggiest sight. We got the right idea. What is this? This is a run of 200 over, oh yeah, duh, I should see that right there. Yes, you're right. Yeah. So it turns out, yes, the slope from 2 to 5, this region, is the same as the slope from here to there, only in the negative direction. Yeah. So this would be, let's see here. Shoot, what do we say? We said that the electric field is the negative slope of the electric potential. So from 2 to 5, so from here to here, the electric field points in the negative x direction, or the negative r direction. Positive slope, and then I have the negative sign here. So I would say that the electric field is pointing in the negative r direction. But then from 5 to 7, I have a negative slope, so the electric field is pointing in the positive r direction. Yay, nay?
Can you say that one more time?
Yeah. So the relationship between the electric field, let me write it over here. The relationship between the electric field and the electric potential is you look at the slope of the electric potential per distance. So if the slope is positive, the electric field is pointing in the negative direction. If the slope is negative, then you have a negative and negative, and so the electric field is pointing in the positive direction.
Where does the negative sign come from?
The one out front, this one?
Yeah.
That one's part of the relationship. Yeah, so it's there. Yeah. It comes into, I think we had a discussion about if shoot, where was it? Yeah, we were talking about the change in potential, like a ball rolling down a slope. And if the potential energy is decreasing, that means the force is in the positive direction. And if the slope is the other way, then it's pushing in the negative direction. And so, yeah, the slope is positive, and so the force pushes in the negative direction. So that's where that negative sign comes in. Too much? Or am I beating the dead horse? There you go, said it'd be the other one. You could go through and do the same, yeah, go ahead.
Sorry. So if, when you said the electric field is the highest, where we have the steepest slope, is that all the way from like 2 to 7, or is it like 2 to 5 and 5 to 7?
I was ambiguous with my question. So if I'm thinking about the magnitude of the electric field, then it's the same magnitude all the way from 2 centimeters all the way to 7. If I were thinking about if I were taking direction into account, then you could argue that it's just from 5 to 7, because that would be the positive one. Yeah, I was ambiguous. Yep. So you could think of plotting, so the electric field, if I wanted to draw arrows, you could think, okay, well, this is a smaller slope. So maybe I draw a small electric field pointing in the positive direction. And then you get a big electric field pointing in the negative, and then you get a big one pointing in the positive direction again. Again, I'm thinking 1D here, right? So you're walking along this 1D axis and the electric field's pointing in the positive direction, pointing in the positive direction. All suddenly, suddenly when you hit 2 centimeters, the electric field is now pointing in the negative direction. You're walking one way and the electric field's pointing the other way. And then you keep walking along your one-dimensional world, and then you see all of a sudden that at 5 centimeters, you look beside you and now the electric field's pointing in the positive direction again.
With the highest the electron's highest potential energy is that R equals 2, though.
Correct.
Okay.
Yeah. Mm-hmm. Yep. Yeah. Mm-hmm. So shoot, what could yeah, I guess somewhat non-physical, but you could think of maybe an electron being located at this 2 centimeter mark. You could think of a proton as being located here at maybe the 5 centimeter mark. That might kind of set up this behavior. At least a little bit. Other questions? Oh, I'm starting to get tired. You guys getting tired? I don't remember what I have next. Probably more questions. Oh yeah, draw graphs, blah, 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 draw more graphs. Oh, okay. Oh, that sounds like a great place to stop. Unless you want to draw more graphs. It's okay. Practice that. You know, practice kind of thinking about it. You can draw your own 1D graph at home and then let's call it quits. Unless you have more questions. Oh, there's an objection. Okay, we can stay. Oh, you're not objecting? Get out of there. I'll see you Monday. Have a good weekend.